In this talk, we are going to deal in more detail with charges and the way they now move. Before, we have just said that the charge was stationary. Now the charge is still at this point, but now it's going to move around a certain circuit. You will follow a certain path. It could be just on a circuit, it could be in the space. Really, this is a very general situation. And this is our charge, as it was before, and this is the trajectory it's going to follow. And this charge is by itself, is the only one we have until now. So there's just a single charge moving somehow in certain place. To solve our problems, we need, once again, just a reference system. This is just the set of coordinates we have talked before when we commented on forces and on vectors. With respect to the system that may be centered in any point of interest, we just draw some vectors to represent the motion of the charge. The first thing to consider is that the charge is at this point at a certain time and is going to move along this path. To represent the point, we just need the distance and the direction, and this is just a vector, is the radius or the distance from this point to this point. And this is going to change the value of this vector, and the orientation is going to change with time. So this is just the first point. But it's not enough to know where the charge is. We also need to know how it's going to move. And for this purpose, we need to know the velocity, not only the position, but also the velocity and the acceleration. And those functions change with time as the charge moves along this path. Here you have the velocity at this point, but if there is acceleration, then the charge will follow the path. Now, this charge is going to produce fields. That means that at a certain point, we are just observing, we are just looking at the charge and trying to measure and sense the fields produced by this charge. Here, once again, we have a distance, we have a vector, a distance vector, and look, for this, we have a capital R vector, is R, and it's a function of this point. Where this charge is, then we have, and where the observer is. And this is really what we are going to treat. The observer receives and senses a field at this point and measures a field at a certain time. This could be using some similar example. When we look at the sky and look at a distant star, we see the light that is reaching us at a certain moment, in a certain instant of time. But this light has to travel a long distance at the velocity of light, at the speed of light, c. So in this case, it takes a time to go from the point where the charge is to the point where the observer is located. That means that what we receive now at this time was produced by the charge at a previous time. There's a time delay. So we say that this time t is retarded with respect to this one. And this is why we use here t and here t prime to say that there is a time delay between those two. Okay, this is just the basic parameters. R prime goes from here to the charge, small r goes to this point of the observer, and capital R goes to this point. With this information, we may now find the electric and the magnetic field at any point of space. This is a very complicated problem, and I just want to give you the result for this. Why is complicated? Because by the time we receive the fields, the charge has moved to a different place. And the values of velocity acceleration are different to the ones we had before. At the end, the fields take this form. That may look complicated, but if you look at the first term of the electric field, you will see that is the one we had before for the electrostatic, for the static case. The second one, the second term, if you see R divided by C, this is just this distance divided by the speed of light. And this is just the time it takes for the signal, for the electromagnetic wave, to travel from this point to this point. So this is just the correction to this term. This is just the rate of change of this field in terms of the delay, times the delay. Those fields decay like fall off like 1 over r squared. But there's a third term here that depends on the c, on the speed of light, and also there's a second term here, which is the second order derivative of the unit vector r, the unit vector in this direction. As the charge moves, this vector changes because now it's pointing in this, and this point will be here, here will be look at this. And outside the bracket, you see this comment, retarded. What is the meaning of retarded? Well, it means that you have to evaluate this field in terms of the charge, but taking into account that it should be at a time that will take into account this delay. So the time t is just retarded with respect to the time at the source and the charge. We will study this formula a little bit later, and if you want to look into it, I advise you to have a look to chapter 28 on the volume, on the first volume on the Feynman lectures on physics. Today is just freely accessible on the internet. This second vector here is the magnetic field, because when the charge moves, not only produces electric field, but produces magnetic field. And you see that they are orthogonal, and also the value of this field is much lower than the value of the electric field, because here you have the speed of light. This is just the expression, the full expression for this problem. Now we are going to look into more details into this term. This is the important one. Why? Because we're going to find, when we just expand this term, that the behavior of this term is different to the previous two. That's the way the expression looks. We have the charge and the second derivative, time derivative of the unit vector, r. Just to make the simple drawing, consider just the charge at a point, the observer here. Those are the vectors we have said before, r and the unit r. Those two vectors point in the same direction. The only difference is that the magnitude of this one is just 1. And the charge is here. So let's assume that the charge is going to move in just one direction. And for simplicity, let's say that the observer is just looking at the lateral displacement of the charge. So the charge is at this point and now moves to this point. That means that in a certain amount of time, interval of time, it will just go along a certain distance. And now the charge is at this point. The observer is here. What happens is that this vector r, that now is pointing in this direction, when the charge moves to this point, now is pointing in this direction. And the unit vectors, that one is pointing in this direction, then it will be pointing in this one. I put here 1 just to show that the magnitude of this segment in this triangle is 1. What is the change in this unit vector as the charge moves? Well, it's just this small vector that is pointing in this direction. In this plot, it's simple to see that this line is parallel to this one. This is just a very simple case, but if you look into the two triangles, you will see that you can gain a lot of information. And this is just the point. Those two triangles have some similarities. And you can immediately write that if you divide this term here, the change in the unit vector, which is this segment of this triangle, by this segment that is 1, you have this ratio. What are the equivalent on this large triangle? Well, it's the displacement and the distance. So this is delta C divided by R. And this is just the term you have here. If you take the second order time derivative of this vector, then this is the same to say that you have to take the second order time derivative of the displacement. And this is nothing more than the acceleration. So at the end, this term immediately gives you that this is, first of all, the acceleration, which is this, divided by the distance. We put here a minus sign to show that if the charge moves in this direction, like this, the vector will go, the field will go in the opposite one. But the most important thing is that this field falls off like 1 over r, inversely proportional to the distance, not to the square of the distance as before. And this is just the basic term. Now, if you look at the bracket, this is related to the retarded term here. And the meaning of this is that we just calculate this value, the one that is here, not at time t, but at the previous time, which is t minus the travel time of going from here to here, which is r divided by c. So everything now is complete, and we can summarize that there is a field component that is in the direction of the motion of the charge, proportional to the value of the charge, inversely proportional to the distance, and directly related to the acceleration. And this is just the basic fact. And this field really just falls off in a different law. And this is just the important part of the story. So only the component of the acceleration that is perpendicular to the line of sight, what the observer is the important one. Here you have the charge moving at a certain velocity. You may also have more than one charge. In this case, you may think of a wire, of just a tube where charges move along. If a charge is just moving with a certain velocity, this is exactly the same thing to say that we have a current traveling a certain distance. And if you take the time derivative here, you will see that the charge times the acceleration is just the time derivative of the current times the length. Here there's a new notation introduced. If we just put the dot on top of the arrow of the vector, that means we are just taking time derivatives of this quantity, of this vector. The first thing we may consider is that if this charge is moving uniformly, there's no acceleration, then this field will not exist. We will be saying that this charge will produce fields, but not the kind of fields we like to have, those that really go very far in the distance. In the second case, when we have many charges, if this is the number of charges per volume times the value of the charge and the velocity, this is similar to say that here we have a charge density and times the velocity. If we take the time derivative, then we have that this is just proportional to the acceleration. So in general, look, the acceleration will immediately produce currents that change in time. And this is just an important factor. In order to have this kind of fields, we need the charge to be subject to acceleration. Here you have one example. Now, assume a charge is moving along this path with constant velocity. maybe like a car driving along a road at a constant speed. Along this path, when the charge moves along the segment, there's no acceleration, so there's no radiation. When the charge reaches this point and just bends, here there's a strong acceleration. We feel this in the car example. So at this point, this charge is going to radiate. It will continue again at this point. So you may have sometimes uniform motion, but if the path is just changing, is winding up and down, then you have acceleration. Here you have a second example. This is a charge that goes back and forth. It just oscillates with a certain frequency. So the velocity is like a swing, goes up and down, and the charge is just reversing cyclically along this path. Since the velocity is changing continuously, that means that this charge will be subject to acceleration and it will be radiating. We will have fields of this kind.